Good morning, student. Today we will discuss Nernst equation, most time topic of the electrochemistry. Now, how to write the Nernst equation? Before writing the Nernst equation, what do you mean by Nernst equation? That means it gives the effect of concentration and temperature on electrode potential. When a standard electrode potential, otherwise standard cell potential, then it is under standard condition. That means the temperature 298 Kelvin, pressure is 1 bar, and temperature concentration is 1 molar. Now these all variable are changes. Then how to calculate the potential of half cell as well as the complete cell? So it gives information from Nernst equation. That means based on Nernst equation we can write. Otherwise we can calculate the electrode potential. Now we have two possibilities. That means half cell and cell. So first we will see how to write Nernst equation for half cell. That means for half cell. Half cell, that means it acts as an anode, second it acts as a cathode. The first possibility we will discuss act as an anode. When half cell acts as an anode, then oxidation reaction take place. That means we can write, suppose this half cell journal, it is converted to Mn plus n electron. Now concentration we don't know, that means it is not unity. Then how to write the Nernst equation? That means half cell potential. N is converted to Mn plus, that means Mn plus equal to standard potential, that means E naught Mn plus minus RT by NF, RT by NF ln Q. Here Q is a reaction quotient, that means concentration of product divided by concentration of reactant. That means now E0 Mn plus minus. Converting this ln comes into log, that means multiply by 2.303 RT by Nm and log. Concentration of product divided by reactant, that means concentration of product, that means Mn plus aqueous divided by concentration of Ms. But we know very well concentration of the solid substance or a liquid at a particular temperature remains constant. This remains constant, that means taken as a unity. That means this is equal to 1. That means remember the species having solid form or liquid form in a reaction, it is taken as always a unity, that means constant. Now we are simplifying this 2.303 RT by F. Now R is 8.314 joule per mole Kelvin, temperature 298 Kelvin, that is 8.314, temperature 298 Kelvin. And F is Faraday constant 96487 Coulomb. Then when this is simplified, it is 0.059. That means this can be written as E Mn plus equal to E naught Mn plus minus from this 0.059 upon n log Mn plus. This is the Nernst equation for half cell. Remember, this is the Nernst equation for half cell when it acts as an anode. Say example. Suppose example, Zn solid gives Zn plus 2 electron. How to write this Nernst equation? So simple. Remember, based on this we can write. So E Zn plus 2 equal to E naught Zn plus 2 minus 0.059 upon N. N means numbers of moles of electron in oxidation half reaction. That means here N is 2. Log concentration of N plus, that means here Zn plus 2. We can write Nernst equation by this way. When half cell acts as an anode. Now second possibility. When half cell acts as a cathode. That means reaction take place when half cell acts as a cathode. Again taking the general reaction, that means N plus N electron, M solid. Now writing directly by this here oxidation reaction, now reduction reaction. That means N plus is converted to M. That means here E N plus is converted to M equal to E naught N plus M. Now minus by this way 0.059 and now log concentration of product divided by reactant. That means here Q. That means product divided by reactant. Now M solid. So again solid having concentration equal to 1. That means 1 divided by concentration of N plus. So when half cell acts as a cathode, then by this equation we can calculate this half cell potential when it is in non-standard condition. Say example, suppose Cu plus 2 plus 2 electron gives Cu solid. This is aqueous. Now based on this we can write E Cu plus 2 Cu Mn plus 2M. That means Cu plus 2 Cu equal to E naught Cu plus 2 Cu minus 0.059 divided by value of N. That means moles of electron here 2 log again 1 concentration of product divided by reactant Cu solid, concentration is 1 divided by Cu plus 2 aqueous. That means this is the Nernst equation for half cell when half cell acts as an anode and when half cell acts as a cathode. Now we will see for complete cell how to write the Nernst equation. When a cell is given Then how to write the Nernst equation? To simple, by taking the example of a linear cell. That is for a cell. How to write the Nernst equation when a cell is given. So first, considering the example of a linear cell. So linear cell we know very well. In a linear cell, zinc half shell acts as a anode, Cu half shell acts as a cathode. That means we know which redox reaction take place in a cell. That means second point is the cell, considering the example of a linear cell. So which redox reaction is taking place? So redox reaction in linear cell is Zn Cu plus 2 is converted to Zn plus 2 and plus Cu. Now Zn is in solid form. Here aqueous, and it is solid. Now how to write the Nernst equation for this complete cell? So similar to half cell, we can write E cell. E cell equal to E naught cell, because here complete cell is there. Minus 0.059 divided by n log. Concentration of product divided by reactant. This will be the product. Reactant, that means Zn plus 2 aqueous. Now C solid. Remember Cu solid, that means the species which is in solid form and liquid form. Concentration is constant, so this is a constant. There is no need to write. Again divided by concentration of reactant. Here Zn is in solid form, that means constant, remember, and divided by Cu plus 2 aqueous. So by this way we can write. Also we know the value of n. Value of n for linear cell in Zn is converted to Zn plus 2 plus 2 electron. So obviously value of n is 2. Now here standard cell potential, how to calculate standard cell potential? So this will be zero. E reduction cathode minus E reduction anode. That means reduction potential of cathode minus reduction potential of anode. That means this cathode. So we know very well Cu act as a cathode. That means Cu plus 2 Cu reduction potential of cathode minus reduction potential of anode. Reduction potential of anode. Anode is Zn. That means Zn plus 2 Zn reduction potential. So by this way we can write the Nernst equation for the cell in short. Suppose the reaction is a general A plus A, B plus B, it gives C plus C, D plus D. Then how to write the Nernst equation? So E cell equal to E naught cell minus 0.059 upon n log C power C into B power B. That means mole will be power form because concentration of product divided by reactant. Then A power A and B power B. Remember this. And the species which is in solid form and liquid, there is no need to write. So this is the general equation for writing the Nernst equation. Suppose taking the example. Suppose equation is given like this. Zn plus 2Ag plus gives Zn plus 2 Zn equation. This Zn solid form, aqueous and solid. So how to write the Nernst equation for this redox reaction? So E cell equal to E naught cell minus 0.059 upon N. So Zn is converted to Zn plus 2 electron. That means the value of N equal to 2 log. Concentration of product given by reactant. That means Zn plus 2 Ag, but Ag is in solid form. There is no need to write. That means Zn plus 2. Now divide by concentration of reactant. Now reactant Zn solid form. There is no need to write Ag plus. But here 2 moles of Ag plus is 2. That means mole will be in the power form. A power and B power will be here Ag plus aqueous and their square. Remember this point. Mole will be in the power form. Now standard cell potential. Standard cell potential is calculated as E reduction cathode minus E reduction anode. Here which act as a cathode? Zn is converted to Zn plus 2 oxidation. That means Zn act as an anode. Obviously Ag act as a cathode. That means which is equal to Ag plus Ag. That means standard reduction potential of cathode minus standard reduction potential of anode. So by this way we can write the Nernst equation for the complete cell. How to calculate the equilibrium constant? Equilibrium constant means K. How to calculate K? Otherwise Kc. So once the cell potential is calculated, then based on this we can calculate the equilibrium constant. So for Daniel cell, we know very well Nernst equation can be written as E cell equal to E naught cell minus 0.059 upon N log concentration of Zn plus 2 divided by concentration of Cu plus 2. Now we know in a Daniel cell, in a Gibb cell act as anode in which oxidation reaction takes place. The concentration of Zn plus 2 increases. Again in a half shell of copper, Cu plus 2 is reduced to Cu. The concentration of Cu plus 2 decreases. That means when a Daniel cell work in a voltmeter reading is continuously decreases, and finally after some time the concentration of Zn plus 2 and Cu plus 2 becomes constant. Zn plus 2 and Cu plus 2 concentration becomes constant. At that time, the cell comes under equilibrium condition when concentration of Zn plus 2 and Cu plus 2 are constant. This becomes constant. Cell comes under equilibrium condition. In this situation, E cell is 0. There is no reading in a voltmeter. That means E cell becomes 0 and concentration of Zn plus 2 divided by Cu plus 2. That means this we can write Kc. That means the equilibrium constant. So by substituting this value, E cell equal to 0, E naught cell minus 0.059 upon n log Kc. That means therefore 0.059 upon n log Kc equal to E naught cell. That means log Kc equal to log Kc E naught cell into n divided by 0.059. So remember this formula to calculate the equilibrium constant. If we know the standard cell potential, then the value of n, and we know the numbers of moles of electron in a balanced redox reaction, and 0.05, substitute the value log Kc will be obtained, and from that by taking anti-log we can obtain the value of Kc. So by this method we can calculate the value of Kc. Remember this formula. Most IMP formula for the calculation of equilibrium constant. Now, relation between the Gibbs energy and the equilibrium constant and the electrical work which is obtained from the electrochemical cell. That means Gibbs energy and electrical work. Now we know very well in the electrochemical cell reaction is spontaneous, redox reaction is spontaneous, and the chemical energy is converted to electrical energy. That means how to calculate electrical work? Electrical work is related with the quantity of electricity passed and the cell potential. That means W electrical is calculated NF. NF is the quantity of electricity passed through cell into E cell. So this is the electrical work. Now, reaction is spontaneous in electrochemical cell. That means the maximum work which is obtained in the electrochemical cell, which is equal to the Gibbs energy, change in Gibbs energy. That means delta G equal to W electrical. But we know very well reaction is spontaneous. That means delta G will be negative. That means negative sign is here. That means the work done in the system of electrochemical cell, which is equal to the change in the Gibbs energy. That means delta G equal to minus NF E cell. Substituting this value, so this relation is comes. Now suppose this cell is under standard condition. Standard condition, that means temperature is 298 Kelvin, concentration of species is 1 molar, and if gas is involved then pressure is 1 bar. Then we can write the standard change in Gibbs energy equal to minus NF E naught cell. Again here we have to remember one point, that standard change in Gibbs energy is an extensive property, and this standard cell potential is intensive property. Remember, this is intensive property, standard cell potential, and gives energy is extensive property. Remember. Now we know relation between the change in Gibbs free energy and equilibrium constant is minus RT ln K based on thermodynamics, that means equal to minus 2.303 RT log K. Otherwise we can write Kc. That means this is the relation between the equilibrium constant and standard change in Gibbs energy. This is the relation between the standard cell potential and the standard change in Gibbs free energy. Remember these two formula for the calculation purpose.